Hello again. We are continuing our discussion of limits of sequences by talking about a theorem called the Squeeze Theorem. So let's get started. Let's say I wanted to know the limit of a sequence as n approaches infinity, and it wasn't something that was particularly easy to find. This theorem will help because what we can do is we can find a sequence that has consistently higher terms than the sequence I was given, and we can find another sequence that has consistently lower terms than the sequence I was given. And if those two sequences approach the same limit, have the same limit as n approaches infinity, then the original sequence must have that same limit. Okay, so let's look at some examples to kind of clarify this. Let's say I have the limit as n approaches infinity of 4n squared plus the sine of 5n all over n squared plus 7. So what I want to do is I want to find a sequence that is consistently higher, every term is higher than this, and a sequence where every term is lower than this, and show that those two sequences have the same limit as n approaches infinity. Well, I know that the sine function consistently goes between values of -1 and 1. So I know that the sine of 5n is always going to be less than or equal to 1. So what I can do is I can say that that original sequence is less than or equal to 4n squared plus 1 over n squared plus 7. Okay, so I can replace that. Also, since I know that the sine function is always greater than or equal to -1, I can replace that sine of 5n with -1 and come up with a sequence that is consistently less or equal to the original function. All right, so I have these three functions here. The blue one is the one I was given. The green one is the one that's consistently higher or equal to, and the red one is the one that's consistently lower or equal to the given sequence. All right, so let's look at the green one, the one that's always going to be bigger or equal to. Well, that's a middle heavy function, and we know how to handle those. The limit as n approaches infinity of that sequence is going to be 4. Then if I look at the red sequence, the one that's always less than or equal to the given sequence, that also is middle heavy, and that sequence as n approaches infinity, that sequence approaches 4. So both sequences, the one above and the one below, approach 4 as n approaches infinity. So what that means is the function that is kind of squeezed in the middle is also going to have a limit of 4 as n approaches infinity. All right, here's another example. If I have the limit as n approaches infinity of n factorial over n to the n. Okay, well, I know what n factorial is. That's n times n minus 1 times n minus 2 all the way down to 2 times 1. I know that every factor of that from n to 2 is always going to be less than or equal to n. So what I can do is I can replace every factor from n all the way down to 2 with n, and I can create a sequence that is going to be greater than or equal to n factorial over n to the n. I'm going to leave the denominator the same, and the reason I'm going to do that is because all of those n's on top can cancel with most of the n's on the bottom, and that will leave me with 1 over n. All right. I also know that every factor of n factorial is always going to be greater than or equal to 1, so I can replace every factor with a 1, and I can come up with a sequence that is consistently less than or equal to n factorial over n to the n. Okay, and if I simplify that, that just becomes 1 over n to the n. So let's look at the limits of those two functions and see if they are the same. Well, there is a bottom-heavy function when I have 1 over n, and so that approaches 0. There's also a bottom-heavy function when I have 1 over n to the n, so that approaches 0. So since both of those limits, the upper and the lower limit, both approach 0, that means that the original function, which is squeezed in the middle, also approaches 0. Okay, so that's two applications of the squeeze theorem. We'll go over more of this tomorrow. So if you have any questions, please let me know, and I will see you tomorrow.